Welcome back to Statistics. I'm Dr. Jeff Crow. Today we're going to talk about assessing normality. In other words, how do you know whether or not the data that you collected came from a population that is normally distributed? To assess this, we will define what we call a normal quantile plot. It's a graph of points with an x-coordinate and a y-coordinate, where each x is from the data, the original data. We're going to rank the data values in order and associate these ranked data values with y values. Each y value is a z-score that is expected if you assume the data is normally distributed. Standard normal distribution. I'll have to explain to you how to find these z-scores. You'll line up the x values in increasing order. Each of these x values will be associated with a y value, which is a z-score. The y1 will be a z-score that corresponds to one over 2n in terms of the area in the normal curve. If we have our data points all lined up, if there are n data points, we'll expect 1 over n area here, and another 1 over n, so the second data point will have 2 over n area to its left. What we'll do is we'll kind of split the differences in here. So we'll have these 2n subdivisions, and we'll take odd values, even values with the denominator of 2n. So if I had 2 over 2n, that would be the same as 1 over n. But if I have 1 over 2n, that's just to the left, that'll be the z-score that I'll calculate that corresponds to an area of 1 over 2n. So in particular, y1 will correspond to an area of 1 over 2n. y2 will be a z-score corresponding to an area of 3 over 2n. We have 5 over 2n for y3 and so on. This will correspond to 2n minus 1 over 2n. So we'll have these n different z-scores that we'll get corresponding to these areas. Let me give you a specific example. Let's have our data. I'll write the data from this card. 0.70, 2.20, 1.64, 1.01, and 1.62. Our first step is to sort the data. We'll write them in increasing order. That would be 0.70, 1.01, 1.62, 1.64, 2.64, and 2.20. Second, n is 5 in this case. So we are going to want 1 over 2n, 3 over 2n, 5 over 2n, 7 over 2n, and 9 over 2n. 2n. n is 5, so 2n is 10. 1/10, 3/10, 5/10, 7/10, and 9/10. We need to find the corresponding z-scores, so that's step 3. We'll do this using the inverse normal operation on the calculator or on the computer. To calculate the z-score that corresponds to an area of 1/10, we'll use the inverse normal function. When I type second distribution, I'll scroll down to the inverse normal. I'll type in the area. On the first one, it'll be 1/10. We'll keep mu equals 0 and sigma equals 1 for the standard normal, and we'll use a left tail. So the z1 that I get after punching all of this in is about negative 1.28. This gives me my first point, 0.70, comma, negative 1.28. For z2, the area will be 3/10 instead. So we'll type in 3/10, and we'll get negative 0.52. So the second point will be 1.01, negative 0.52. Z3, we're using 5/10 now for the area. And we get a z-score of 0. So at 1.62, we'll have 0. Now the remainder of these will be symmetric because of the symmetry in the standard normal curve about 0. So z4 will be positive 0.52. And so that gives us the point 1.64, 0.52. And finally, the point z5 will have a positive 1.28 for the z-score. And so we'll have 2.20, 1.28. We need now to plot these points to see what the graph looks like. To plot these points, I'm going to enter two lists. The first list will be the original data sorted as we have here. So 0.7, 1.01, 1.62, 1.64, 2.2. In the second column, I'm going to enter the z-scores just as we found them. Negative 1.28, negative 0.52, 0, 0.52, and 1.28. Next, I'm going to plot these things. Second stat plot, I'm going to do a plot of list 1 and list 2 in stat plot. That's just above the y equals button on the TI-84 Plus. And I'm going to use a scatter plot of just these points. I'm going to turn the plot on. And you can see the plot, if you set the window needs to include the data, but not much else. So I'm going to make my minimum x value be 0, and my maximum x value to be 3. The minimum y value I'll choose to be -2, and the maximum y value to be +2. And the plot that I get looks something like this. And that's more or less linear, from which we would conclude then that the data is reasonably normally distributed. So the procedure for testing normality begins with plotting a histogram. If the histogram looks something like this, then fine, it kind of looks like the data is more or less normally distributed. But if the histogram does something like this, then the data is probably not normally distributed. So if the histogram departs substantially from a normal distribution, then we'll conclude that the data is not normally distributed. It must largely appear mound-shaped. If it departs substantially from mound-shaped appearance, then it's not normal. We identify outliers. If there are 2 or more outliers, then we'll assume the data is not normal. Then we make the normal quantile plot, which we just did on the previous example. If the plot departs from a straight line in a substantial way, then the data is not normal. And finally, step 4. Apply these criteria loosely if there is only a small amount of data, but apply them strongly for a large amount of data. As an example, if your data is fairly normal, like this, you expect the quantile plot to look more or less linear. If the data was uniformly distributed, then the normal quantile plot, instead of being linear, will make a little S hook like that. And if the data is skewed like this, then the normal quantile plot may do something like this instead of being linear.
On this next problem, I'd like to do something with the spreadsheet. I'm going to type in, say, arm circumferences, and our data will be 40.7, 44.3, 34.2, 32.5, and 38.5. 5 pieces of data. The question I have is, does this data come from a normal population? So the very first thing I want to do is I want to sort the data in increasing size. So I'm going to sort this in column A in ascending order. So it's all been ordered now. Note that n is 5. So we're going to need values with 1, 3, 5, 7, and 9. And I would like to take this number and divide by 10 all the way down. These will be the ones that I have to calculate the z-scores from. The norm inverse is what you use in a spreadsheet. The number that we're going to use is this to the left here, with the mean of 0 and a standard deviation of 1. We don't need the last entry. And we'll paste this formula down. Now all we need to do is plot the 2 pieces of data, these 2 columns, together. So we'll insert a chart. And the sort of chart that we'll use is an XY scatter plot, like this. And note that this looks rather linear in nature. And so we'll conclude that the data is normally distributed. Let's try another set of data. This data is earthquake depths. And let's suppose it's in kilometers, 17.3, 7, 7, 8.1, and 6.8. 8.1 and 6.8. Again, the first thing you want to do is to sort the data in increasing order. 3, 5, 7, 9, and 5 pieces of data means we'll take these numbers and divide by twice 5, which is 10. We'll paste this down. Norm inverse. Take this. Calculate our z-scores for the normal quantile plot. And we'll plot these 2 columns together, inserting a chart. Not a bar chart, but an XY scatter chart. And from this chart, it looks like the data is not even close to normally distributed. And so that will be our conclusion, that it is not normally distributed. Let's try another data, in this case brain volumes. 1027, 1029, 1034, 1070, 1079, 1079, 963, 1439. In this case, the number of data values is 8. So we use n equals 8. We want to sort the data first. So data sort. And we'll put odd numbers, 1, 3, 5, 7, 9, 11, 13, and 15. We'll take these numbers and divide by 16, twice n. 2 times 8 is 16. So divide these numbers by 16 this time. Use the norm inverse function. These will be the areas on the standard normal curve. So we'll paste those down. And then all that we have to do now is plot these two columns by inserting a chart. What kind of chart? Don't want a bar chart. I want an XY scatter plot. And if you look at these, let me change the view so you can see this a little better. We'll change the view on the spreadsheet, that is. View, zoom. I'll do this at 100% now. You can see that we can ignore these data. These are just zeros plotted beyond the range of our data. This is the actual data here. Should have highlighted this differently. But this does not look normal. This does not look like a straight line. This data comes from a straight line. And so our conclusion will be not normally distributed.
For the normal approximation, to the binomial distribution, we have to keep in mind to use a continuity correction. We can only use the normal curve to approximate the binomial provided NP as at least 5 and NQ is at least 5. In this case, we must use a mean of NP and a standard deviation of the square root of NPQ. Remember that for the binomial distribution, we're checking the number of successes to be between two values, where these two values are whole numbers. They can't be fractions. They can't have things with non-trivial decimals. They can't be 1.72. They have to be 1, 2, 3, 4, or 0, and hence whole numbers. The continuity correction would be to find the probability of A minus 0.5. You always back half off from the left side and half off from the right side in the other direction. So this is the continuity correction here. The idea is that the binomial distribution looks like these histograms, where A is the middle of one of these and B is the middle of another. In order to include the entire bar within the histogram, we have to go half a unit back, A minus a half, and half a unit forward, B plus a half, like this. As an example, suppose the owner of an apartment complex must install 25 water heaters. From past experience, a particular brand works for him. It's accessible and affordable and of sufficient quality. Is guaranteed for only 5 years. But based on experience, will last 10 years with a probability of 0.25. So about a quarter of them will last at least 10 years. So A. What is the probability that 8 or more will last 10 years? So let's think about this. We have a binomial experiment. Either the product will last 10 years or more, or it won't. We have success and we have failure. And we're performing this experiment supposedly independently n equals 25 times. The probability of success is 0.25. The probability of failure is 0.75. If we calculate NP, that's 1/4 0.25 of 25. That's definitely bigger than 5. 4 goes into 25 about 6 1/4 times. So, and since Q is even larger, NQ will also be bigger than or equal to 5, which means that we may use the normal distribution to calculate the probability that we seek. We want to know the probability that the number of successes is at least 8 or more. To use the continuity correction, we'll back off one and go 7.5 and higher. The mean that we will use is 25/4, and the standard deviation that we will use will be the square root of 25 times 0.25 times 0.75, and we'll type that in just like that, not rounding anything until the end. We'll use the normal distribution, normal CDF. The lower bound will be 7.5. The upper bound just needs to be really large. So I'll make the upper bound 1,000 The mean, I'll make 25 divided by 4. And the standard deviation, what we've written here. And the probability that I get is 0.281, and I'll round it here, 19. How well did we do compared to an actual binomial probability? For the binomial probability, I'll take 1 minus binom CDF where the number of trials is 25. The probability of success is 0.25. The x value will be 7. I'm calculating, first of all, the binomial CDF will calculate the probability from some number lower. I want the probability of 8 or higher. So what I'll do is I'll take the probability of 1 and subtract the probability of getting 7 or lower. So 7 is the x value. And the actual value that I get here is 0.2735. So this is the normal approximation to the binomial probability. And this is the actual binomial probability.